right, so first thing I want you guys to do is grab a graphing calculator and graph this function, and then pick some point and then zoom in. Okay. So I'm going to do the same thing. And I'll probably do mine on Desmos just because I like Desmos. So what do we have? X cubed minus 7x squared plus 5x plus 2, right? All right. So anybody have a particular point we want to zoom in on? How about this local max right here? Yeah. Let's zoom in on that local max. So does it look any different now?
Nope.
No, not really.
No.
How about now?
Nope.
Not really, no.
No, not really. How about now?
No.
It's gonna be a fun game we're gonna play today. How about now?
Nope.
Are we there yet?
How about now?
Still no.
I'm seeing something.
Teaching you guys what
look
it's like to
like
have
that.
children. How about now? How about now?
No.
No.
Doesn't look any different? It looks a little different. I mean, it's like,
I mean, it's flattening.
yeah, it's flattening. How about now?
Just flatter.
Yeah.
How about now?
Just getting flatter.
Getting flatter. Yeah. How about now? Getting flatter. How about
Yeah.
now? Still getting flatter. How about now?
Almost looks like a line there.
Almost, huh? Almost looks like a line. How about now? I don't even know where that max was. Kind of looks like a line. How about now?
Kind of looks
Well,
like a line.
now it's gone. How about now?
Oh, no.
Yeah, I mean,
Yeah, it's just getting flatter.
right, it's just getting flatter, and it just ends up looking like a straight line. True?
True.
I mean, we've zoomed in pretty darn far here now. I don't know what the I can't even see the scale for how far we've zoomed in, but I mean, back here, this was 1/1000 from here to here. So I mean, we zoomed in even more than that. Yeah, so each of those boxes is like 1/100,000th of a point there, right? And it begins to look just like a line. What if I pick some other point? I mean, that point's going to take the longest because that point is a local max. But even if I picked some other point, like let's pick this point here at around x equals 2, let's say. If I plug in if I look at the point around x equals 2, it already looks like a line, doesn't it? I haven't already zoomed in very much at all, but it already looks like a line. And so that's one of the things we want to talk about with derivatives, is that if we take a derivative, right, a derivative at a point is just a tangent line, right? That gives us a slope of a tangent line. And so at a point, if we zoom in really close, so if we look at a very, very small range of x values, our derivative is effectively almost exactly the same as the line that we're looking at, or as the curve that we're looking at, right, on that very small interval. We call that idea linearization. And we use this idea of linearization to approximate the value of a function at certain values, at certain points, by using the tangent line. Okay. So, and I know we've used the tangent line a few times already. We used point slope form, right? Like y minus y1 equals m times x minus x1. So if we were talking about some point on there, let's say that that point would be a comma f of a, right? Well, then point slope for a comma f of a would be y minus f of a, right? Y minus the y value equals the slope at a, f prime of a, times x minus a. True? Would you all agree that that would be the equation of the line at some point a?
Yeah.
Yeah. And so that line on a very small scale for very small changes in x is a good enough representation of the function that we can use this linearization, so we call it a linearization, to approximate the function on that interval. And so that's what we're going to do today. We're going to use linearization and the idea of the tangent line and the tangent line approximation to approximate values of functions. Okay? Because on a very small scale, it's basically the same. So if we just add the f of a over, we end up with this formula right here. The linearization, and we call that capital L of x, is equal to f of a plus f prime of a times x minus a. And so what we're going to do is we're going to use the a value is going to be a value of x that we are able to evaluate our function at. And then we're going to use the x value as the value that we want to know. So we're going to take the function f of x equals the square root of 1 plus x, and we're going to approximate that function at x equals 0.02 to approximate the square root of 1.02. And we're going to be able to do it without a calculator. And then we're going to see how close our approximation actually is. Does that idea sort of make a little bit of sense? I'm going to talk more about it before we get started. Say that again?
So it's like an approximation of the derivative? Is that kind of what it is?
I mean, it's not an approximation of the derivative. We're using the derivative as an approximation of the function.
And what does the function find then?
Well, I mean, the function finds whatever the function is. So like this function that we're going to first look at is the function of the square root of 1 plus x. And so we're going to use that function to approximate this value. But we're going to be able to do it without a calculator, which is nice because, you don't have a calculator for everything on the AP test. And also, this is one of the ways that your calculator does approximate things, is it uses these linearizations that come from derivatives. So there's a couple of important pieces of this to remember. First is we need to figure, we're going to, like you're going to see, I'm going to give you guys things like square root of 26. So we're going to approximate that. So the first thing you need to be able to do is you need to be able to come up with a function that you are going to use for finding that value. So we're looking to find the square root of 1.02. And so we're going to use the function f of x equals the square root of 1 plus x to do that. And so there's a value for x that we could plug in so that we would know what this is very easily. What value of x, or what value could x be, so that we know the square root of 1 plus x very easily.
0.02.
Well, okay, so we want to find the square root of 1.02, but there's a value of x that makes the number inside of here very close to this, but that we can actually square root easily.
0.
Yeah, 0. So that's why we've written x equals 0 here. So that value that we choose that can be plugged into this function to give us something very close to this is called our center of approximation. And we represent that using the a, and that's the a up here. So we're going to say a is equal to 0, right? A is equal to 0. And our x value then, what x value would we need to plug into this to get the exact value? That'd be 0.02, right? And so all we're going to do is we're going to use this tangent line equation, f of a plus f prime of a times x minus a. And we're going to plug in these values, and it's going to give us a very good approximation for the actual value of the square root of 1.02. Does that sort of make sense?
So what is the L of x equation up there? What does that one do?
This is what we're going to use, and this is what we call the linearization equation, and it's the one that will approximate our function. So we're going to say that capital L of x is approximately equal to f of x, right? And it's only a good approximation when the difference between these two values is very small, and the difference between 0 and 0.02 is pretty small. True?
Yeah.
So because that difference is such a small difference, we can use the linearization to approximate the function because we can find it at 0. We're going to find it at 0, and then we're going to approximate it at x equals 0.02 because they're so close to each other. So what we'll do is we'll say f of 0.02 is approximately equal to L of 0.02. And so we'll then plug that in, and that should be f of a. Well, what's f of a? F of a is the square root of
1.
Yeah, I'm going to write it all out just so we have it there. But it's the square root of 1 plus 0, which is 1, plus f prime of a. Well, we've got f of x, so we need to find f prime of x. What's f prime of x equal to? Like 1 over 2 root 1 plus x, right?
Yeah.
So what's f prime of a? F prime of a ought to be 1 over 2 root 1 plus, if we're plugging it in at 0. And then times our x minus a. X is 0.02 minus a, which is 0. And that should be a very good approximation for the square root of 1.02. So we'll evaluate that out. That gives us 1 plus, this becomes just a half, right? 1/2 of 0.02. Half of 0.02 is 0.01. And we're going to say that 1.01 is a very good approximation for the square root of 1.02. Now, we might think, well, that just seems kind of stupid. We got 1.01. That's, I mean, if somebody asked you, what's the square root of 1.02? You might be like, no, it's about 1.01, right? It just seems like, doesn't seem like that's a good approximation. But if we go in and take a look at what the actual square root of 1.02 is, we'll see, it's 1.00995, right? And so, 1.01, that rounds up to 1.01. It's off by what? 5, what are those? 100,000ths, right? So it's a pretty darn close approximation of the actual value of square root of 1.02. You guys see that?
Yeah.
So it's pretty good, right? It's not that bad. It's actually a pretty good approximation. And that's all we're going to do. We're going to do a few of these today. And we're going to do some other stuff afterwards, but we're going to do a few of those right now. Does that make sense? Anybody have any questions on that? On the idea of it or how we executed it?
So we have to make up equations. Like eventually we're going to have to make up the equations, the f of x equations.
True. Yes, correct.
Okay.
Yep. And none of them are going to be exceptionally difficult. This is actually, it may seem like a complicated thing or a difficult thing, but it's really not going to be that bad. I promise.
Okay.
Yeah. All right. So we are going to try to approximate the cosine of 1.75 without a calculator. And we're going to, obviously, since it's cosine of 1.75, we're going to use the function cosine of x. And we're going to use the approximation at pi over 2, which, we should know that. Look and see what pi over 2 is. Pi over 2 is pretty darn close. Not super close, but it's fairly close to 1.75, right? They're off by what is that, 1800ths, right? No, fairly close. Not as close as the last one, 1.0 to 1.02, but still pretty close. So we're going to say that f of x is equal to cosine x, and we're going to use the linearization at 1.75. So f of 1.75 ought to approximately equal L of 1.75. And now we're just going to use our linearization. So our linearization says f of a. Well, our center of approximation, a should equal pi over 2, since that's the value. We know the cosine of pi over 2, right? We can evaluate that one, so that one's close, and we can use that as our value. So we're going to say f of a is cosine of pi over 2, and then plus f prime at A. So what's f prime of x? Derivative of cosine is?
Negative sign.
Negative sine. So we're going to have plus negative sine of pi over 2 times our x value, which is 1.75, minus our a value, which is pi over 2. Good or no?
Good.
All right. So what does this equal? First off, what's the cosine of pi over 2?
0.
0. So we got 0 minus the sine of pi over 2. So what's the sine of pi over 2?
1.
1. So we got minus 1 times this 1.75 minus pi over 2, which we just distribute the negative through, and we get that the cosine of 1.75 is approximately equal to pi over 2 minus 1.75, which doesn't seem, it seems a little weird again, probably. Would you guys agree that that seems a little bit weird again?
Yeah.
That doesn't seem like a great value. So let's go in and take a look and see what that actual value is. Pi over 2 minus 1.75. So that comes out to be negative 0.179203, blah, 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 blah. And what were we actually looking for? We were looking for the cosine of 1.75. Well, it's pretty close, right? I mean, we're off by, looks like 1/1000th. So that's a pretty darn good approximation. Good enough, I think, for pretty much any case we want. Do you guys agree?
Yeah.
Yeah, not too bad at all. So, any questions on that?
Not yet.
Not yet. That's good. No questions yet. All right. Let's see if we can use a linearization to approximate the square root of 26. So now we're going to have to come up with our own function and our own values that we're going to use, but shouldn't be too bad, I hope. What do you think the function we'll use is?
Square root. Oh.
Should be the square root of x, right? Yeah?
Yeah.
Everybody good with that?
Yeah.
And what value that's very close to 26 do we know the square root of?
25.
25. So we will say that we will center our approximation at a equals 25 because we know what the square root of 25 is, and our x value will be 26. Okay, sorry about that. So if we want to find the square root of 26, that's f of 26, right? And f of 26 should approximately be equal to L of 26. And L of 26 should be f of a, so that will be the square root of 25, plus f prime of a. So now what's the derivative of f of x? F prime of x is 1 over 2 root x. And so we have the square root of 25 plus 1 over 2 times the square root of 25, and f of a plus f prime of a, times x minus a. Everybody good with that setup?
Yeah.
Good. So square root of 25 is 5, plus 1 over 2 root 25, that's 2 times 5, or 1/10 of 1, or we got 5 and 1/10, 5.1. And once again, like, it doesn't seem like it's a very good approximation. That's like the kind of thing you'd make up if somebody said, what's the square root of 26? You'd be like, I don't know, about 5.1. But if we go in and take a look, square root of 26 is 5.099. So it's again off by 1/1000, right? Which is a pretty darn good approximation. Any issues with that? Any questions on that?
No.
All right, let's do another one. You guys want to try and do this one on your own?
Sure.
All right, I'll give you guys, I don't know, 2 or 3 minutes and see if you guys can work through this one on your own. Ready to go. So what's the function, what's f of x that you're going to use for this?
Cube root of x.
Cube root of x, good. And we're going to need f prime of x, so let's figure out what's f prime of x. What's f prime of x? This is x to the 1/3, so that should become 1/3 x to the negative 2/3, yeah?
Yeah.
Yeah.
And what's the a value that you're going to center your approximation at that you know the cube root of?
125.
125.
125 sounds good, since we know that the cube root of that is 5, and then our x value is obviously 128. That's our value there inside the cube root. Everybody good with that?
Yeah.
So the cube root of 128 should equal f of 128, which should be approximately equal to L of 128. And L of 128 ought to be f of a, so cube root of 125, plus f prime of a, so that'd be 1/3 of 125 to the negative 2/3 times x minus a. So far good?
Yeah.
Yeah.
Okay, so cube root of 125, like we said, is 5 plus 1/3 of this. So 125 to the negative 2/3 is 1/125 to the 2/3, which should be what? 1 over
25.
1/25.
25, right? Cube root the 125 first to get 5, then square it, so 25. And then times what? 3?
3.
3 and our third will cancel out. 5 and 1/25. What's 5 and 1/25? 1/25 is a decimal. If you want to write it as a decimal, it's 5.04. 0.04. All right, so we got that the cube root of 128 is about 5.04. Is that what you all got when you did it on your own?
Yep.
And if we go in and take a look, cube root of 128 is 5.0396, so 968. So that looks like we're off by less than 4/10,000ths, right? 3,200 thousandths off on that one, about. So pretty darn close to the actual value again. Any questions or issues with any of this?
No.
All right, so you're going to have some problems to practice with this tonight. We're going to now take this and apply it to pretty much any function and to approximate the change in a function. Okay? So what we're going to do is we're going to take the dy and the dx that we have when we take a derivative, right? The derivative of y with respect to x is dy dx. And we're going to treat those as different variables. So dy is one variable and dx is a different variable. And we're going to say that dy is the change in y. And we're going to say that dx is the change in x. And so we know that dy dx, the derivative with respect to x of a function, is just f prime of x. So if we split those dy and dx's up and multiply by dx to both sides, we get dy is equal to f prime of x times dx. And when we do it in that manner where we've got these separate variables, we call this a differential. And a differential is just a way to approximate the change in a function when you have a very small change in the other variable, in your independent variable. And so we're going to look for small changes in y based on a very small change in x. So what we're going to do is we're going to see about how much the function x to the 5th plus 37x changes. This isn't going to be exact, but about how much it changes if we go from x equals 1 to x equals 1.01. And we're going to use the same idea of the tangent line approximation. We don't have to do the full linearization formula for this. We can just use the fact that we know the derivative and we know how much the x value is changing to find the change in it. Does that make sense to everybody?
Wait, so how did you move the d of x?
So we're just treating these as separate variables, dy, dx as separate variables, dy meaning a change in y and dx meaning a change in x. And we just, just multiply both sides by dx.
You can do that?
We can do that when we are talking about very small intervals on which our function is changing. Yes, because when we have that small interval, our tangent line or our derivative is a good, like we noticed before, it's a good approximation for our function. And so we can use that tiny bit to look at this as a change in y versus a change in x and separate them out.
Got it.
Somebody else was saying something too. What was that? Everybody good?
Yeah.
All right. And you'll note that when we move into some of the stuff we're going to do once we're done with applications of the derivative, when we start talking about integrals, we're going to have these like small changes in x variables. These dx variables will be sitting by themselves within our integrals, which you don't need to worry about now, but it's basically we're going to be kind of looking at this same idea when we move into integrals, but don't worry about that yet. So our small change in y, dy, ought to equal the derivative of this, 5x to the 4th plus 37, times whatever the small change in x that we have is. So we want to know what happens as we go from 1 to a change of 0.01. So from 1 to 1.01, how much does our function change? Well, it changes by 5 times 1 to the 4th plus 37 times that change in x times 0.01, which, what is that? That's 5 plus 37 is 42. So 42 times 1/100th is 4200ths. So that's not exactly how much this function would change, but it's close enough. It's a close enough approximation to how much the y value changes, and it should be as accurate as any of these other ones that we did earlier, where they were all off by 1,000th or less than 1,000th. This will be about the same.
So that 0.42 represents the change in y across x equals 1 and the change in x is 0.01. Is that what we just found?
Yep. This is how much y changes as x goes from 1 to 1.01. No, it's not exactly the same. It's about how much y changes as x goes from 1 to 1.01.
So we were just given the change in x. Would
Yep.
we normally have to try and
No,
find it out?
it'll usually be given to you.
Oh, okay, cool.
I mean, it will be given. If they want you to find the change in y, it will be given to you. They may give you the change in y and say y changes by about this much. How much did x change by? And then you just, you'll just have a value over here and you'll solve for the dx value. But yeah, you'll be given either a dx or a dy in all of these.
Okay.
Or it'll say something like, hey, about how much does y change if x goes from 2 to 2.02? Well, then you should be able to figure out what that change in x is just by subtracting them, right?
Yeah.
Cool. All right, let's do a couple more of these, and then we'll call it quits for the day, because we're not going to have time to talk about today's last topic that I was hoping to talk about. So we want to find dy, the differential dy, and evaluate it for x and dx. So what is dy equal to? Dy ought to be the derivative of sine 3x, which Hopefully by now you're able to do the little chain rule piece of that in your head. That's my hope. What's the derivative of sine of 3x?
3 cosine 3x.
3 cosine 3x, and we have a dx there, right? And so we're now looking at x is pi, dx is negative 0.02. So dy ought to equal 3 cosine of 3x, which is 3 pi, times negative 0.02. And what's the cosine of 3 pi? It's the same as the cosine of pi, right? And the cosine of pi is
-1.
-1. So we got 3 times -1 times negative 0.02. And that gives us a positive 0.06. Everybody good there or no?
Yeah.
Spectacular. Let's do another one. So this time our function looks a little different. It's actually not a function, right? It's x plus y equals xy. This is an implicitly defined equation, but the same rules will apply. Anytime I differentiate the x or the y, I'll get a dx or a dy. Okay. So we should end up with dx plus dy equals, and how do I differentiate x times y? Using the
Product rule.
So it's x times the derivative of y, or x dy, plus y times the derivative of x, or y dx. Good or no?
Good.
All right. So we've got an x value of 2. We've got a dx value of 0.05. We're looking for dy, but we're going to have a little bit of a problem here. So let's first solve for dy, right? Maybe that'll make things a little bit easier. If we solve for dy, we could write this as dx minus y dx equals x dy minus dy, and we could factor out the dy. In fact, we could also factor out, might as well factor out the dx so we don't have to multiply multiple things by 0.05. So dx times 1 minus y equals dy times x minus 1. And so we'd have dy is equal to dx times 1 minus y over x minus 1. Everybody good with that?
Yeah.
All right. So when we try to plug things in, what's the issue we have? Dx is 0.05. That's not a problem. 1 minus y is 1. Oh, well, there's the problem. We don't have a y value, do we? We have an x value.
No.
But we don't have a y value. How are we going to find a y value then? We just pick whatever we feel
Plug
like.
it back in.
Yeah, we're going to have to plug it back in up here. So we know that x equals 2, and we know that x plus y equals xy. So if x is 2, then 2 plus y equals 2y. Everybody would hopefully agree with that, just by plugging in x equals 2 to that.
Yeah.
And what does y equal? Subtract a y, you get y equals 2.
Yeah.
Yeah.
So we'll plug in that 2. And now we end up with dy is equal to 0.05 times -1 divided by 1, or just negative 0.05. Any problems with that? Everybody okay with that?
Nope.
All right, cool. Let's do one more. This time we're going to sort of apply it in a sort of real world situation. It's not really, because how am I really going to make the radius of a circle increase from 10 to 10.1 meters? But that's fine. If we had a circle that was increasing from 10 to 10.1 meters and we wanted to estimate the increase in the area, what's the equation that we would use to do that? What is the area of a circle?
Pi r squared.
Pi r squared. So using a linearization or using a tangent line means we're just using these differentials for functions that look like this. So what does the change in area equal? It should equal the derivative of this, which is 2 pi r dr. And what did our radius start at?
10.
Started at 10. And what does our dr become? Our change is 0.1.
0.1.
And so all we do is plug it in. The change in the area ought to be 2 pi times 10 times 0.1, which gives us what?
2 pi.
About a change of 2 pi meters squared. Don't forget the units if there's units that should be attached to it. Any questions or issues with that?
So how did you get the derivative equation? Like I get the 2 pi r, but oh, never mind. I see. Because 2 pi r is just the derivative, and then
Right.
dA is the dy.
Yep.
And
We just got different
dr
variables.
is the dx. Okay.
Yep. Just different variables, but same idea. Yep.
Yeah. Okay. See that now.
Good, good. Any other questions on that?
So the dr just came from like when you use implicit and you didn't have the value, you got to write like dy dx, and it's like the same thing here. Is that what it is?
I mean, effectively, yeah, it's very similar to that. It's just the same idea we were doing here with the differentials, right? The derivative of the function times the change in that variable is equal to the change in the other variable.
Okay.
Everybody good with that?
Yeah.